So, why are we spending billions and billions of dollars to build quantum computers? Well, the real answer probably isn't what you've heard. It has nothing to do with being faster or creating some kind of super AI. It's about a fundamental problem, a problem we literally can't solve any other way. It's about necessity. Okay, let's just dive right in. The devices you and I use every day, they are absolute miracles of engineering. I mean, AI can whip up breathtaking art from just a sentence. Our supercomputers can simulate things as complex as the entire global climate. So, with all that incredible power, why on earth are we pouring so many resources into building an entirely new, almost alien kind of computer? To get to the real answer, you first have to appreciate just how mind-blowingly successful our current computers, what we call classical computers, really are. I mean, their history is just this incredible, breathtaking story of progress. Think about it. We went from these machines that filled an entire room running on fragile vacuum tubes to powerful little transistors that could fit on your fingertip. And those led to microprocessors that put a computer on every single desk. And now we have GPUs and specialized AI chips that perform trillions of calculations all at once. It's just an unbelievable achievement. And yet, for a very specific but really, really important class of problems, even the most powerful supercomputer on the planet just grinds to a halt. And this isn't a matter of just building them bigger or faster. No, they hit a fundamental mathematical wall. That wall, it's called exponential scaling. And here's how to think about it. Imagine you have a puzzle, and for every new piece you add, the total difficulty doubles. So 2 pieces is twice as hard as 1. 3 pieces is 4 times as hard. Well, by the time you get to just 300 pieces, you would need more computer bits to solve it than there are atoms in the entire known universe. No amount of silicon is ever going to overcome that. So what kind of problems scale like this? Well, the very ones that could unlock the next generation of science. We're talking about things like designing a brand new drug molecule from scratch, or creating a material that can superconduct electricity at room temperature, or truly understanding what's going on inside a next-gen battery. For our classical computers, these problems aren't just hard. They are fundamentally impossible to solve perfectly. And this is the crucial point, right here. For these exponentially hard problems, our best supercomputers are really just guessing. They're making approximations. Now, they get close, which is incredibly useful, don't get me wrong, but they can never perfectly represent the true physical reality of what's happening. They're describing the shadow on the wall, not the actual object that's casting. And this brings us to the absolute core of the issue. The reason our classical computers fail is because they're trying to describe a world that doesn't speak their language. The universe, at its most fundamental level, it just doesn't operate on a system of simple ones and zeros. So here's the heart of the conflict. On one side, you've got our classical approach, using bits, fighting this brutal exponential wall, and in the end, only approximating reality. But on the other side, you have nature itself. And nature handles all this quantum complexity effortlessly because that's its native language. It is reality. You see, nature uses properties that simple bits just don't have. One of them is interference. Think of it like waves in a pond, right? When 2 wave crests meet, they make a bigger wave. When a crest meets a trough, they cancel each other out. Well, quantum possibilities can do the exact same thing. They reinforce the right answers while canceling out all the wrong ones. A bit can only be on or off. It can't just cancel another bit out of existence. And the other property, well, it's even stranger. It's called entanglement. This is where 2 or more quantum particles get linked up into a single, inseparable system. What happens to one instantly influences the other, no matter how far apart they are. This incredible web of deep correlation is something classical systems just cannot represent efficiently. In fact, it's the very thing that causes that exponential scaling problem in the first place. Now, it is so important to remember that scientists didn't just invent these weird ideas for fun. Quantum theory wasn't just dreamed up in an armchair somewhere. It was forced on them by reality itself. Experiments back in the early 20th century kept giving results that classical physics said were completely impossible. The math only came after the experiments because it was the only way to make sense of what they were actually seeing. And this all led to a major philosophical shift. See, a quantum computer isn't just a faster calculator. It's actually a tiny, highly controlled piece of nature that we set up to mirror a problem we want to solve. Then we just let it evolve according to the laws of quantum mechanics, the same laws the universe always follows, and we measure the result. We are, in essence, letting nature compute for us. Okay, so this brings us to a really crucial point. We have to separate the genuine scientific reality of what quantum computing is from the mountain of media hype that's all around it. You've probably heard the big claims, right? That quantum computers work by trying every single possible answer at once through infinite parallelism, or that they're going to replace your graphics card or unleash some new super AI. But the scientists who are actually building these things will tell you that's a common misunderstanding. The real power isn't about trying everything at once. It's about cleverly using that interference property we talked about to cancel out all the wrong answers and amplify the few correct ones. So what are they, really? While they are highly specialized scientific instruments, the best way to think about them is less like a smartphone and more like the Hubble Space Telescope. I mean, you wouldn't use the Hubble to check your email, right? But for looking at distant galaxies, it is absolutely irreplaceable. Quantum computers are exactly the same. They're built for a specific set of tasks that nothing else in the world can do. It's all about the right tool for the right job. For tasks like AI, graphics, weather forecasting, our classical supercomputers and GPUs are and will continue to be the champs. They are brilliant at those jobs. But for simulating large molecules, for discovering new materials, or for breaking certain types of encryption, problems that are rooted in that quantum entanglement, you need a different tool. You need a quantum computer. And this, right here, is the single most important takeaway from all of this. The motivation was never about simply being faster. It was about fidelity. It was about truth. We built them because the language of bits and bytes, as powerful as it is, simply cannot describe certain fundamental truths about our universe. To represent reality, we had to build a machine that operates on reality's own terms. So we'll end on this thought. This whole journey into quantum mechanics forced us to abandon centuries of classical intuition about how the world is supposed to work. It showed us that reality is far, far stranger and more complex than it appears, which leads to the question, as we explore it further, what other common sense ideas are we going to discover are just approximations of a much deeper, weirder truth?